If you've checked out the videos that I did for chapter 1 and 2, you'd know that index questions are dealt with the moment we finish a particular topic. This chapter, however, I might have gotten a little bit carried away with making videos and basically trying to explain various topics of the periodic table, because periodic table is still one of the most favorite things in chemistry that I liked from the beginning, and then I continue to like even now. So in this video, we will be dealing with the in-text questions. So what would be the IUPAC name and the symbol for the element with atomic number 120? So with respect to the IUPAC nomenclature, you have the name, the abbreviation, and the corresponding digit. So for 120, you have 1, 2, and 0. All we need to do is put these letters side by side, the root words side by side, and then add the letters em in the end. So un by un is for 1, by is 2, nil is 0. So un by nilium. And the symbol will be the first letters of all these three, which is U, B, and N, and U will be capital. So until the name is being confirmed by the IUPAC, we will use these letters to name or to denote these elements. How do you justify the presence of 18 elements in the fifth period of the periodic table? So n equals to 5 for the fifth period. And based on the energy levels, you have the orbitals which are available are 5s, 4d, and 5p. The reason 4d is after 5s is because of their energies. Similarly, if you notice 5d will not be here, it will be 6s, and then you'll have 5d orbital. So, and that in turn is based on the energy levels of these orbitals. If you haven't learned about it, do check out the atomic structure. It's much more clearer over there. So you'll be able to understand this better. So the available orbitals are 5s, 4d, and 5p. So the total number of orbitals, 5s will have 1 orbital, d orbital generally has 5, p has 3. So that totals up to 9. And the number of electrons that can be filled is 18. So 18 elements are present in the fifth period, just the double of 9. 9 was the 18. So you have 18 elements, and that's why you have 18 elements in the fifth period of the periodic table. If you notice, you have in the first period, you have just 2 elements. I think we discussed that in detail, but the first period has 2 elements because n equals to 1. You only have the s orbital. And so only 2 electrons can fill into that. And so you have 2 elements. So the number of elements in each period is also dependent on the the number of orbitals which are available in each case. The third question, the elements 117 and 120 have not yet been discovered. In which family or group would you place these elements, and also give the electronic configuration in each case? Now, first of all, I think when this book was given, or when this question was given, all the elements had not been discovered. Now we know elements up to 118. We know their names, and we've assigned their, they've been discovered or created, synthesized. So 117 is actually here, which is tennessine. So atomic number of radon is 86. That's the previous, that's the one before 117. That's the noble gas before 117. So 117 minus 86 is 31, which means 31, the number of electrons that have to be filled are 31. So the electronic configuration would be 5f14, 6010, 7s2, and 7p5. So if you order it in terms of their energies, it would go 7s2, be 7s2, then you'd have 5f14, and then you'd have 6d, 10, and then 7p5. And since its outermost electrons are filled up in the p orbital, so, and it has 5 electrons, which means it will be under halogens. So that's why here you have 117, which is tennessine. The next atomic number, the next one is 120. So the last element that we know right now is organazon, which is 118. And so only 2 electrons have to be filled up, which means, so first of all, organazon is in the 7th period of the periodic table over here. So which means the next one will be filled up into the 8th period, which does not exist because the element has still not been completely discovered yet or synthesized. Anyways, so the electronic configuration of the elements Z equals to 120 would be organazon's electronic configuration, 8s2. To know in detail as to how to write the electronic configuration of various elements, you have to check out the electronic configuration in the previous chapter and revise that again. But this is the basic idea. Considering the atomic number and position in the periodic table, arrange the following elements in increasing order of their metallic character: silicon, beryllium, magnesium, sodium, potassium. Sorry, phosphorus. Sorry, it's phosphorus. Anyways, so here, if you notice, metallic character generally decreases across a period, which means these elements, so these elements are non-metals, these elements are metalloids, and these are all metals. So here you have been given phosphorus, silicon, silicon, beryllium, magnesium, sodium, and phosphorus. So here, if you notice, phosphorus is over here. So phosphorus, silicon. Then you have, so phosphorus and silicon is clear. Now, because the periodic table decreases across the period. Now, the reason we have beryllium before magnesium and sodium is because beryllium is above magnesium. So the metallic character increases on going down the group. So you have beryllium at the top, which means it's more metallic than it's less metallic than magnesium and sodium. And so you have phosphorus, silicon, beryllium, then followed by magnesium, and then the last or the most metallic one of the lot is sodium. So that's how you have the order: phosphorus, silicon, beryllium, magnesium, and sodium. So this is because metallic character decreases across the period and increases down the group. Which of the following species will have the largest and the smallest size? Now, you've been given 2 elements, magnesium and aluminium, and their respective ions. We need to figure out which is the biggest one and which is the smallest. Now, let's first compare magnesium and aluminium. Since they are, aluminium is to the right of magnesium. Aluminium will have a smaller radius compared to magnesium. Right. So the magnesium atom itself will be bigger than the ions which exist. Now, if you notice, if you remember, we discussed about the cation size. Now, magnesium has only lost 2 electrons, whereas aluminium has lost 3 electrons, which means the effective nuclear charge is going to be much higher. So the smallest one of the lot will be aluminium ion, Al3+, and the largest species will be magnesium, because from the left to right, the atomic radius is going to decrease. So magnesium will have the largest size compared to these these 4 species, and aluminium Al3+ will have the smallest radius or smallest size. Now, the first ionization enthalpy value of the 3rd period elements, sodium, magnesium, and silicon, are respectively 496, 737, and 786 kilojoules per mole. Predict whether the first ionization, delta H, that is the ionization enthalpy value for aluminium, will be more close to 575 or 760 kilojoules per mole. Now, first of all, let's look at their values. So it is 496 and 737 and 786 kilojoules per mole. Those are the respective ionization enthalpies. Let's look at the periodic table. Okay, so here we've been given the ionization enthalpy values of 3 elements, right? That is sodium, magnesium, and silicon. Okay. Yeah, so sodium, magnesium, and silicon. Okay, and they have values of 496, 737, and 786 for silicon. We need to figure out the value of aluminium. Will it be closer to 575 or like 760? Now, the reason, first of all, let's see this. Here you have 496 as its ionization enthalpy and 737 for magnesium. The reason there is a huge increase is because the s orbital is completely full, and half full and completely full, especially for in case of s, because it's completely filled, it is much more difficult to remove that electron, and so its value is quite high. Now, in case of aluminium, the value will be closer to 537, and it's 575 because of the shielding of the nuclear charge by the 3s orbital. So 3p will not get enough. So the ionization enthalpy of aluminium will be more closer to 575 than it will be to 760 kilojoules per mole. Also, there's only one electron in the p shell, so it's easier to remove. Next, which of the following will have the most negative electron gain enthalpy and which will have the least negative? Now, the element with the most negative electron gain enthalpy in the periodic table is chlorine. Technically, we'd expect fluorine to have it, but because of repulsions in the 2p orbital, it does not have that highly negative, and its small size, it does not have a very high highly negative electron gain enthalpy. So elements which are on the right side of the periodic table will, except for the noble gases, will have a highly negative electron gain enthalpy, and so chlorine will have the highest electron gain enthalpy because it's at this extreme. That fluorine is lesser than chlorine because of the small size. Sulfur will have more negative electron gain enthalpy. So the least electron gain enthalpy in that set is phosphorus, because the electron gain enthalpy becomes more negative on the right side of the periodic table than the left. Now, using the periodic table, predict the formulae of the compounds that might be formed by the following pairs of elements. Now, this particular topic, I think you should have learned it in your previous classes. All we're going to do is use their valencies. There was a crisscross method. So we have silicon and bromine. Silicon, Br, right? They are the respective symbols of these elements. Valency of silicon is 4. Valency of bromine is 1. And generally, we have the positive atom on the left side, and the negative one will be, that is the one which will have a negative charge generally, is on the right side. So silicon 4, so Si1, Br4, but since it's 1, you don't need to write it. So Si, Br4. If you do want to have a detailed video about the crisscross method and how to write the various formulae, do comment and I will make one. So the valencies are considered. Again, aluminium's valency is 3, sulfur's valency is 2. So the valencies are just exchanged and put underneath. So Al2S3. That's it. So we're just going to be considering their symbols and their respective valencies, and we are going to crisscross them. And this is all, again, dependent on their location and their electronic configuration. Valency is going to be dependent on that. The oxidation state and covalency of Al in AlCl H2O5 taken 2 plus the same. Now, the oxidation state and the covalency of aluminium in these two cases is different. And in its oxidation state is +3. I believe we'll be learning about the oxidation state of complexes at a later point in time. But its covalency is 6. So this is because the covalency of an atom is the number of covalent bonds that that particular atom can form, whereas oxidation state is with respect to the number of electrons that it has lost or gained. So aluminium's oxidation state in this case is Al3+. I think you'll be doing this calculation in detail when you learn about coordination compounds. I don't know if it's in this year or next one. Anyways, it's to do with the characteristic of the substance it has been bound to. Covalency is, of course, the number of elements or number of bonds it has formed. So 5 plus 1 equals to 6. So the covalency of aluminium over here is 6. So they are not the same. Show by a chemical reaction with water that Na2O is basic and basic oxide, and Cl2O7 is an acidic oxide. So when the easiest way to remember the fact that there are acidic and basic oxides is their reaction with water, or when they are dissolved in water. So when sodium oxide is dissolved in water or reacts with water, it leads to the formation of sodium hydroxide, which is a base. So sodium oxide is the basic oxide. However, the oxide of chlorine is a basic oxide, is an acidic oxide because it leads to the formation of perchloric acid, which is highly acidic. Here in this equation, chlorine is in its 7 oxidation state, whereas it can exist as a 1 oxidation state, but that's not as acidic as this one. So with this, we finish the in-text questions of this chapter. In the next video or in the coming set of videos, we'll be discussing the textbook questions of this particular chapter.